So we're going to look at one last example of using the chain rule to find a derivative. Now we're going to actually find the derivative of this function y in two different ways. So the first thing that we're going to do is to try and use the chain rule along with the quotient rule to find this derivative, right? Your first thought should be, when you look at a function like this, to find the derivative we need the quotient rule, right? It's one function, one differentiable function divided by another. And we can do that, right? So the way that the quotient rule works is we have a top function, a bottom function, start off by finding the derivatives of each, and then use those with the chain rule. So I'm going to call my top function, right, this whole thing, I'll call this g of x. And the denominator function, I'll call this h of x. And I'll start off by doing a little bit of scrap work. So g of x is the function e to the 3x squared plus 4x. That whole exponent is a polynomial. And h of x is the denominator function, which is x to the 10th power plus 6x to the 7th plus 9x cubed, all being raised to the 4th power. All right, now we have to find the derivative of each one before we can use the quotient rule. Well, how do we find the derivative of these two functions? They're not just as simple as e to the x or x to the 4th power. It's something more complicated, right? And so because we have a e raised to a whole nother polynomial, or a whole polynomial raised to the 4th power, this suggests to us that we're going to need the chain rule to find the derivative of g and the derivative of h, which is fine, right? So what we do here is we need to identify our inner function. In this case, our inner function, what's making this more complicated here is the exponent, 3x squared plus 4x, so that's going to be our u. The derivative of that would be 6x plus 4, okay? And so I rewrite our original g function in terms of u, and by the chain rule, to take the derivative of that, I take the derivative with respect to u first. So the derivative of e to the u with respect to u is just e to the u again, but then I need to multiply that whole thing by u prime. All right, and plugging everything in, I get that my derivative is going to be e to the original exponent power, e to the 3x squared plus 4x power, times u prime of x, so times 6x plus 4. All right, I'm going to have to do the same thing over here for h of x. I need to use the chain rule again. So I identify my inner function. My inner function here is the polynomial inside the parentheses. I probably shouldn't call this u again because I've already used u, but fine. Let's call this u1 over here, and we'll call this one u2. Okay, so u2 is the function x to the 10 plus 6x to the 7 plus 9x cubed. The derivative of that would be 10x to the 9th power plus 6 times 7 is 42x to the 6th power plus 9 times 3, that's 27x to the 2nd power. All right, I rewrite my h in terms of u. So h of x would be the function, now it's going to be u raised to the 4th power, or u of x to the 4th power. And the chain rule says that to find the derivative of this, I take the derivative with respect to u, so 4 times u to the 3rd power, and then I multiply by u prime. And plugging that back in, we get that h prime is equal to 4 times my original u function, x to the 10th plus 6x to the 7th plus 9x cubed, times u prime. All right, so times 10x to the 9th, I'm running out of space, plus 42 x to the 6th plus 27x squared. Oof. All right, there it is. It's a mess. Okay, but now that we've done our scratch work, it's just a matter of plugging everything into the quotient rule. So remember, the quotient rule tells us if you have a function of the form g over h, then the derivative is going to be bottom times the derivative of the top. So that would be hg prime minus top times the derivative of the bottom, gh prime, all divided by the original bottom function squared. Okay, so plugging everything in, using the scratch work that we just did, we have h times g prime. That would be x to the 10 plus 6x to the 7 plus 9x cubed to the 4th. That's h times g prime. So times e to the 3x squared plus 4x times 6x plus 4, right? That's h g prime minus g times h prime. So minus e to the 3x squared plus 4x times, now we times h prime, so times 4, x to the 10 plus 6x to the 7th plus 9x cubed. I see now that I made a little mistake here when I was plugging everything back in. I should have raised this u of x function to the 3rd power. So there should be a 3 here. Okay, fix that, and then we multiply it by, I'm running out of space, but then we multiply by 10x to the 9th plus 42x to the 6th plus 27x squared. Oof. All right, oops, sorry. That's hg prime minus gh prime. All of that's going to be divided by the original bottom function squared. So x to the 10 plus 6x to the 7 plus 9x cubed to the 4th is our original bottom function, and we're going to square it. Right, or you could just think ahead and say, well, I'm squaring this function raised to the 4th power. You multiply the exponents and just say, this is this polynomial raised to the 8th. And what a mess this is, right? I mean, this is horrible to look at. We don't really like using the quotient rule just because it's a little bit more messy than the product rule or some of the other rules that we've used. And so a great thing about the chain rule is that it actually allows you to find any derivative that normally would require the quotient rule without using the quotient rule. So that's what I want to do next, is to show you how we can use the chain rule to sort of forget about the quotient rule altogether. So we're going to solve this exact same derivative again, right? But this time we're going to use the product rule rather than the quotient rule. All right, so what are we going to do here? We need to, well, if we're going to try to get rid of the quotient rule, then we have to get rid of the quotient, right? Get rid of the fraction. And so what we can do is we can rewrite our original function, getting rid of the fraction by moving the denominator up to the top. And we're allowed to do that if we change the sign on the exponent, right? So I can rewrite this as my numerator, e to the 3x squared plus 4x, times the denominator raised to the negative 4 power instead of the positive 4 power. X to the 10 plus 6x to the 7 plus 9x cubed raised to the negative 4 power. All right. Do we hopefully agree that this function is equal to this function? It's the same function, I've just rewritten it without the fraction. And so we can see now that this is easy enough to do the derivative of using the product rule because it's a product of two differentiable functions. Okay, so to do that, just like before, we're going to give each of these functions a name and find the derivative. So I'll call this my g of x function. That's e to the 3x squared plus 4x. And I'll call this my h of x function. X to the 10 plus 6x to the 7 plus 9x cubed raised to the negative 4 power, and I'll take the derivative of each as scratch work. Luckily for us, we already did the derivative of the g function on the last page. I'm not going to go through and do the chain rule again because right, we already have the work right up here, right? So the derivative of g, since g is the same function here, I can just copy it from before. So it's still going to be e to the 3x squared plus 4x times 6x plus 4. Okay. Now what about h? H is not quite the same function that we had before, right? If we look at our h of x function from before, it was that polynomial raised to the positive 4 power, and now it's being raised to the negative 4 power. Okay, but you could do the same thing. It's going to be the same u function on the inside. I'm just going to go through and not actually go through the substitution of putting in the u. At some point, you just sort of do it enough and realize what's going on here. So to find h prime, we take the derivative with respect to the inner function. Okay, so that means we move the -4 down in front. We leave the inside alone. And then subtract 1 on the exponent. So -4 minus 1 is going to give me a new exponent of -5. And then I need to multiply by u prime. So multiply by the derivative of the inner function. The derivative of that inner function would be 10x to the 9th plus 42x to the 6th plus 27x squared. Okay, so that's my h prime function. And now finding the derivative of y just requires the product rule. Right, so y prime would end up being g times h prime plus h times g prime. Okay, so our derivative is g times h prime, e to the 3x squared plus 4x times -4. Notice I put parentheses around there so it's clear that I'm not subtracting, I'm multiplying, times x to the 10 plus 6x to the 7 plus 9x cubed raised to the -5 times 10x to the 9th plus 42x to the 6th plus 27x squared. Okay, that's gh prime. And I add hg prime. So h times g prime. X to the 10 plus 6x to the 7 plus 9x cubed to the -4 times g prime. E to the 3x squared plus 4x times 6x plus 4. Oof. All right, there it is. Now, this is also messy. I'm not saying it's necessarily any better than our original derivative over here, but I mean, at least it's not a fraction. It took a little bit less writing. And also you're maybe less likely to mess up the product rule than the quotient rule, because with the quotient rule you have to be careful about which term is being subtracted. And with the product rule it doesn't really matter which one you do first so long as you match g with h prime and h with g prime, because it's got addition in the middle, addition is commutative. So I would recommend when you have a quotient rule problem, you can always rewrite it as a product rule problem, right? Even if it wasn't something like this example here where we have a function raised to a power. Even if it was something else, like, I don't know, let's say we had the function e to the 2x plus 5 divided by cosine of 5x, something like that. You could use the product rule to solve this as well. You don't need the quotient rule. You would just need to rewrite that function as e to the 2x plus 5 times cosine of 5x to the -1 power, right? Take this whole denominator, move it up to the top by putting an exponent of -1. Right now you can use a product rule on these two functions. You will have to use a chain rule, but the product rule works. Okay, ending this video. Bye.